Here we've got a calculation which involves adding a strong base, potassium hydroxide, to ethanoic acid, a weak acid. And we've got to work out the pH at 3 different points. We've got to work out the pH firstly before any potassium hydroxide has been added. And then after we've added 8 centimetre cubed of potassium hydroxide to this weak acid. And then thirdly, when we've added an excess of this strong base to the weak acid. Now, this practically what we're going to do, then we're adding this potassium hydroxide from a burette, as it says in the question, to 25 centimetre cubed of ethanoic acid in a conical flask. So if we have a look at this in terms of a pH curve, what we've got then is pH on my y-axis and volume of base on my x-axis. We've got a strong alkali, weak acid titration curve. So it looks a bit like this. So point A is before any potassium hydroxide has been added. So we're looking at this point here. That's point A. Point B is when 8 centimetre cubed of potassium hydroxide has been added. So we'll say that's around here. And when 40 centimetre cubed potassium hydroxide has been added, and we'll say that's going to be around here. That's my 3 different points of my pH curve. The first thing we're going to look at is what pH would be after or before any potassium hydroxide has been added. So here we're simply working out the pH of a weak acid. That's all we're doing. And to work out the pH of a weak acid, then my hydrogen ion concentration is equal to the square root of the Ka times the HA. So here my hydrogen ion concentration then is equal to, the Ka is given in the question, let's see what it is, 1.74 times 10 to the minus 5. And my acid, weak acid concentration, well, that's given here, 0.16 moles per decimetre. So when you do that calculation, you should get a hydrogen ion concentration of 1.66 times 10 to the minus 3. And then obviously we just minus log to the base 10 the answer. And that gives me a pH of 2.78. So that's my initial pH. So that's the pH simply of a weak acid. Part B now involves working out the pH after adding strong alkali to an excess of a weak acid. Now we said in the buffer action video, if I've got strong alkali added to an excess of weak acid, we're in effect forming a buffer. So in this particular one, we need a buffer calculation. And when we're doing a buffer calculation, we need to look at the following equation. H plus is equal to Ka times HA over A minus. So that's the equation we're going to use here. But what we've got to do now is work out these values. Now what we've got is, I've got my HA is reacting with my hydroxide ions to form A minus plus H2O. And I started with 25 centimetre cubed of a 0.16 mole per decimetre solution of ethanoic acid. So from this we can work out the moles of my HA. And when you work out the moles of this, you should get 4 times 10 to the minus 3 moles. I'm now adding hydroxide ions, and we need to work out the moles of hydroxide ions that we've added. We can work that out from the concentration of my OH minus and the volume. And 8 times 10 to the minus 3 times 0.21, that would give you 1.68 times 10 to the minus 3 moles. So I've added, in effect, I've added 1.68 times 10 to the minus 3 moles. So all these hydroxide ions are going to react because I've got an excess of my weak acid. But this now is going to go down by 1.68 times 10 to the minus 3 moles. And that's going to give me then 2.32 times 10 to the minus 3 moles of my HA. Now, for every mole of HA which reacts, a mole of A minus forms. So this is going to increase by 1.68 times 10 to the minus 3. So now I've got my HA moles and my A minus moles after the addition of my hydroxide ions, and I can simply plug these numbers into here. So let's do that. So my hydrogen ion concentration then is equal to my Ka, which is 1.74 times 10 to the minus 5, multiplied by my HA, which is 2.32 times 10 to the minus 3, divided by 1.68 times 10 to the minus 3. That gives me a hydrogen ion concentration of 2.4 times 10 to the minus 5 moles per decimetre. And again, when I minus log to the base 10, the answer should get a pH of 4.62, and that would be the pH at point B. Again, I have been asked this question before. How do you know that you've got to use this equation? It's because if you've got a strong base added to an excess of weak acid, then you have to assume a buffer has been formed, and if you've got a buffer, you have to use this particular equation. Let's have a look at part C. So part C, we've simply got an excess of strong base. Or strong alkali. So what we've got here is we've got my HA has reacted with my OH minus, again to produce A minus plus H2O. We already know that we've got initially 4 times 10 to the minus 3 moles of HA. I've added now, if we work it out, 40 centimetres cubed. So I'm adding now 40 centimetres cubed of potassium hydroxide. So we work out the moles, which is 40 times 10 to the minus 3 times 0.21. Moles is concentration times volume. When you do that, you get 8.40 times 10 to the minus 3 moles. What you should be able to see there is now that all of the HA has reacted. So all the HA moles have reacted. So I've got no HA left. It's not a buffer anymore because I have no HA present. What you're going to have then is you can have an excess of hydroxide ions. For every mole of this hydroxide ions that react, a mole of HA reacts. So you will have the moles of hydroxide ions in excess is going to be 8.4 times 10 to the minus 3 minus the number of moles of HA which has reacted with it. So that's going to give you 4.4 times 10 to the minus 3 moles. The amount of A minus that you've got there is not relevant because that's not going to affect the pH. So the only thing which is relevant here is the moles of hydroxide ions. What you do then is you do a calculation. This is very similar to the calculation that we looked at when we were mixing strong acids and strong bases. We had an excess of strong base. We've got to work out the concentration of hydroxide ions, and that is the moles, which is 4.4 times 10 to the minus 3, divided by the volume, which is 40 plus 25, which is then 65 times 10 to the minus 3. And that gives you a concentration of 0.0678 moles per decimetre. What you now need to do is you need to work out the hydrogen ion concentration, and that is equal to Kw over OH minus. Now the Kw is given, well, it's not given in this question, but if not given, we're going to assume that the Kw is equal to 1 times 10 to the minus 14. So Kw, 1 times 10 to the minus 14 over my hydroxide ion concentration, 0.0678. That gives me a hydrogen ion concentration of 1.48 times 10 to the minus 13 moles per decimetre. And then I again simply minus log to the base 10 that answer, and you get an answer of 12.83. And that's the pH at point C on my titration curve. So this one is quite a tough question, because what it's actually asking you to do is look at 3 different methods on how we can work out a pH. Firstly, we worked out the pH of a weak acid using an equation that you need to be able to remember. H plus is root Ka times HA. The second one is getting you to realise that we've got a buffer solution, because we've got strong base added to an excess of weak acid. And then the third one is just simply when we've got an excess of strong base. So it's very similar to a strong acid plus strong base calculation where we've got an excess of strong base. So there are my 3 different pH values that match the 3 different pH values there on this graph.